Okay, yesterday we were discussing about, the fundamental particles. The first we started with fundamental particles, that is electrons, protons and neutrons. Then we discussed about the composition of the particles which are in uh, the nucleus, that is protons and neutrons. Now, and also we discussed about one atomic mass unit. One atomic mass unit, or 1U. It is equal to what? 1/12 of C612. 1/12 of C612. So that is said to be one atomic mass unit. The value of one atomic mass unit is found to be 1 point. It is found to be 1 point. How much it is? 1.66 into 10 to the power of minus 27 kg. This is the mass of, or one atomic mass unit. When we are comparing the, now mass of proton will become how much? It will be equal to 1.00727 U, and the value of mass of neutron is equal to how much? 0. The value of neutron is 1.00866 U, and mass of electron in terms of U, atomic mass unit, is 1 point, 0. It is 0.0005 and 5 U. So now mass of proton is how much? 1.66 into 10 to the power of minus 27 kg. Mass of neutron is 1.67 into 10 to the power of minus 27 kg, and it is 9.11 into 10 to the power of minus 31 kg. These are the values of proton, electron, proton and neutron. Next one, we'll go to the atomic number. What is atomic number? Atomic number is number of Z. That is what? Number of protons in the nucleus. Number of protons in nucleus is said to be, number of protons in nucleus is said to be atomic number. The next is atomic mass. Atomic mass or mass number. Atomic mass or mass number. What is that? Number of protons and neutrons. Number of protons and neutrons Number of protons and neutrons is said to be atomic mass or mass number. So we write n equal to what? A equal to Z plus n. A equal to Z plus n. So if you want to calculate the number of neutrons, n equal to what? A minus Z. So that is the way we can calculate. So in periodic classification table we write XZA, where Z is, so example, so we can write C612. So what is that? Z equal to 6, A equal to 12, and n is number of neutrons, which is also equal to 6. Now I will quickly define what is isotopes. What are isotopes? Isotopes means atoms of, that is same elements but different atomic mass. Like example for this is C612, C613 and C614. These are the example of isotope. Same atomic, that is same atomic number but different atomic mass. They are said to be isotopes. Now what are isobars? Isobars means having the same mass number. Example is what? N714 and C614. Same of different atoms of different elements but having same mass number is said to be isobars. Next is isotones. What are isotones? Isotones means same number of neutrons. Means N714, C613. There are same number of neutrons. Here N in both the cases is how much? Same number of neutrons. That is how much? 7 number of neutrons are there in both the cases. Is it clear? So that is isotopes, isobars and tones. Okay, isotopes, isobars and isotones. Next one is size of the nucleus. How to find out the size of the nucleus? They have given the formula. Size of the nucleus is given by, what is that? R is equal to R naught into A to the power of 1/3. What is R naught? R naught is the radius of the nucleus. So radius of the nucleus. So that is how much? R0 equal to how much? 1.2 into 10 to the power of minus 15 meters. 1.2 1.2 into 10 to the power of minus 15 meter. That is the radius of the nucleus. Okay, that's the radius of the nucleus. 1 second. That's the radius of the nucleus. 1 point. How much it is? Radius of the nucleus. So it is coming around. It is almost all femto. 10 to the power of minus 15 is nothing but it is femto. Is it clear? Okay. So quickly take a screenshot. We'll go to the next point. Now 10 to the power of minus 15. See, 10 to the when I write 10 to the power of minus 9, it is nanometer. Minus 12 is picometer. Minus 15 is femtometer. Okay, FM, femtometer, 10 to the power of minus 15. Now, going ahead quickly to the next one. Is it clear, all of you? Is this clear?
Yes, sir.
Okay. Now, going ahead with the next concept. Now, with the next concept, that is so size of the nucleus we found out, that is R equal to R naught. So this was actually found out using the formula volume of the, see, they have considered the nucleus as a sphere and the volume of the sphere is 4 by 3 pi r cube. They used that formula and they found out that R equal to R naught into a to the power of 1 by 3. Now A is the atomic mass or mass number. Next is mass energy equivalence relation. Mass energy equivalence relation. Mass energy equivalence relation. In mass energy equivalence relation, what they have done? They have used E is equal to mc square formula. Okay, where C is m is the mass and C is speed of light, that is 3 into 10 to the power of 8 meter per second. Next one is what? Binding energy. What is binding energy? Energy required to bind the two nucleons. What are nucleons? Nucleons means protons and neutrons together are known as nucleons. Okay, protons and neutrons together are known as nucleons. What is binding energy? Energy required to bind two nucleons. Okay, energy required to bind two nucleons. To bind two nucleons. Energy required to nucleons or separate them. Okay, or separate them. That is said to be binding energy. Then what is nucleon? Nucleons means protons and neutrons together are known as protons and neutrons together are known as neutrons together are known as nucleons. Okay. So now binding energy formula we have this. What is binding energy formula? To find out the binding energy, first we'll find out the mass defect. What is mass defect? Mass defect is calculated using delta M formula. So what is the formula here? Delta M formula. So what is that? Here delta M equal to calculated mass minus actual mass. Okay, Z into MP plus A minus Z into Mn minus capital M. Okay, so this is said to be mass defect. That is, this is equal to calculated mass minus actual mass. This actual mass we get from the periodic classification chart. Again, that mass, how do we find out? Using spectrograph or spectrometer experiment. So we get the isotopes and we find out the mass percentage and all. Using that method, we find out the actual mass of the atom. Now, next is binding energy. Binding energy formula is given by EB is equal to what? EB equal to delta MC square. The next concept is about binding energy. Binding energy per nucleon. Binding energy per nucleon. So binding energy per nucleon is given by EBN equal to what? EB divided by A. This is the binding energy per nucleon. Next one is there is a graph. Binding energy per nucleon versus mass number. There is a graph that is binding energy per nucleon versus mass number. Okay, so when you look at that graph, from that graph we have two main features of the two features of that graph. What are the two features? the features of that graph is, number one, we came to conclusion that the atomic number less than 30, between 30 and 170, between 30 and 170, the binding energy per nucleon is constant. Binding energy per nucleon is constant. This is the first point what we got. The second point is lower. Binding energy per nucleon is less. For what? Is less for A less than 30 and A greater than 170. Okay, is less than for EBN, that is binding energy per nucleon is less for the atoms or elements whose atomic mass is less than 30 and greater than 170. These are the two features. Now quickly we'll go to the conclusions. What are the conclusions of that particular graph? Okay, that is very important. Now, if you take down, just take a screenshot, we'll go to the next point. Take a screenshot, we'll go to the next point. Done? Okay. So, now next one, we have the conclusions. What are the conclusions of this particular graph? We came to conclusion that is nuclear force is attractive force. Okay, the force number one, it is an attractive force. The force between the nucleons is a attractive force. Number two, second one is what? There is a constancy between both of them. So we came to the conclusion that it's a short range. The force is a short range, means 10 to the power of approximately 10 to the power of minus 15 and 10 to the power of minus 15. Okay, and 10 to the power of minus 16 meters. Okay, 10 to the power of, it is very, very short range and attractive force. These are the two conclusions of second conclusion of this. And so for very heavy nucleus, so what we got the conclusion, that means above 170 and below 30. Okay, so we came to one more conclusion, but that is A is greater than 170. A is 170. Example, that is, suppose we have taken A equal to 240. So that means what? Fission is possible. What is fission? Fission means breaking of a heavy nucleus into small intermediate nucleus. Breaking of a heavy nucleus into small intermediate nucleus is said to be fission. The next one is what? When A is less than or equal to 10. When A is less than or equal to 10, that is what? That is A is so that means, example you can take less than or equal to 30. That is, we can take A equal to 10. That means fusion experiments are possible. What is fission? Fission means breaking of a heavy nucleus into breaking of a heavy nucleus into small intermediate nucleus with the emission of enormous amount of energy. Emission of enormous amount of energy. With the emission of enormous amount of energy, that is said to be fission. Okay, then what is fusion? We'll write the definition for fusion here. So fusion, what is fusion? Fusion means combining small nucleus to form a bigger nucleus. Okay, this happens, this type of experiment takes place. Example for fission here I am writing, that is atom bomb or nuclear reactor. These are the examples, and for this the example is sun and star. Okay, sun and star, these are the examples of sun and star. These are the examples of nuclear fusion. Once again, nuclear fission means breaking of a heavy nucleus into small intermediate nucleus with the emission of enormous amount of energy. That is fission, that happens in atom bomb and nuclear reactor. Fusion is combining small nucleus to form a bigger nucleus. That is, example is what? Sun and star are the best example for that. Now, we'll come to the nuclear forces. That is, the nuclear force exists between the nuclear forces. There are 3 points here to be discussed. Nuclear forces, like the scientists started discussing, the scientists started trying to understand what are the forces, or what is the force which is keeping the protons, neutrons together inside the nucleus. So when they started studying, like we have different types of forces, like gravitational force we have, electrostatic force we have, different types of forces we have. Okay, so then they came to a conclusion that there is some force which exists between proton proton, okay, neutron neutron, and proton neutron. Okay, that force is known as a nuclear force. They defined a new force. Second one, what is that? That is an attractive force. It's not a repulsive force, it is a attractive force. Number three, what is that? It is a short range force, means it is limited to a short range, which is limited to 10 to the power of, that is around how much? 0.8 Fermi. Okay, 0.8 Fermi, very less. Okay, that is 10 to the power of minus 15 to 10 to the power of minus 16 meters. Next, quickly we'll go to radioactivity. Any doubt in this? Quickly take a screenshot. We'll go to the next point. Is this clear, all of you? Yes. Okay, going to the next point. Done. Take the screenshot. Take the screenshot. We'll go ahead now. Now here we have radioactivity. See, the first radioactivity was discovered by Henry Becquerel. The concept of radioactivity was first formed by Henry Becquerel, A.H. Becquerel. So just I will take 1 or 2 minutes to explain what exactly he found out. Now Henry Becquerel, actually he was doing experiment on fluorescence phenomena. Fluorescence means delayed photoelectric effect. He was doing experiments on fluorescence, Fluorescence, fluorescence and phosphorescence phenomena. He was doing it. That means delayed photoelectric effect. You know what is a photoelectric effect? So delayed photoelectric effect is known as fluorescence phenomena. So he was doing some experiment, means we have to expose the salt to the sunlight, and the electrons will be emitted. Those are taken by the, that is detected by the photographic plate. Later on we develop the photographic plate. That was the experiment. Actually, it will take some time. So when he was doing some experiment, there was actually rain for consecutive days, like 3 days. So then there was no sun. So he kept a new pack of photographic plate he kept the new pack of photographic plate in a in the table, in the drawer of the table. Then he was busy with some other work. Now later on when the rain was not there, or when the sun came, then at that time what happened, he wanted to use the photographic plates for the same fluorescence phenomena concept. Then when he opened the packet, all the photographic plates were already exposed in the same pattern. Then he understood that something happened actually. This is a new packet. Nothing. If it was exposed, only 1 or 2 photographic plates would have exposed. Photographic plates means like X-ray sheet, man, in simple words. Now what happened is, he thought like maybe all the photographic plates got exposed. Something has happened. Now he started studying those salts which are present in the drawer. Then he came to conclusion that was a radioactive element. Okay, it was a radium, which is a radioactive element. He found out radium. So that is for which he got the Nobel Prize. Now after that, later on, uh, Madame Curie. She started working on radioactive elements, the concept of radioactive elements. Now Madame Curie is only a woman who got Nobel Prize in both physics and chemistry. She got Nobel Prize in both in physics and chemistry. She is the only lady on the planet who got Nobel Prize in 2 different subjects. Okay, so what was her contribution? Madame Curie started her research work with Pierre Curie, her husband. Okay, Pierre Curie. So both started working. Actually, they started in a car shed, car parking area in that, because earlier, there was very less encouragement for the research work. So you have to do privately. So she started doing research work in like in a garage with her husband both. So they found out a element called polonium. They actually belong to Poland. Okay, so they found out an element called polonium, named after their country. So for which they got a Nobel Prize. Then after that, Marie Curie died in a tragic accident. Then she continued. She did not leave the research work. She continued. The first Nobel Prize she got together. That is husband and wife. They got together. The uh, second Nobel Prize was with the daughter. The daughter, she carried the research work with her daughter. That is Juliet Curie. Juliet Curie, both of them continued the research, and they found out the radioactivity concept and all. So, but it was very late. They both of them got exposed to these radiations, radioactivity, that is radioactive element radiations, because of which both of them they were affected by cancer, and they later on died because of cancer. But they found out there was a lot of contribution by both Madame Curie, Marie Curie, and Madame Curie and Juliet Curie. Okay, really it helped a lot, because of which we are able to save many lives. The chemotherapy, the cancer treatment which we are doing today, and the X-ray. Many after that many discoveries took place, and because of which we are able to save many people's life of many people. Now, what is the alpha? Here we will discuss about alpha and beta decay. What happens in the alpha decay and beta decay? Any doubt in this? This was the history of radioactivity. Next comes, that is alpha decay, beta. What are the decays? We'll study about alpha decay, beta decay, and gamma decay. So first alpha decay. Alpha is what? Alpha particle means. Alpha particle is a nucleus of helium, nucleus of He24. The second one is beta particle. It's a beta particle. Beta particle is what? Beta particle is a fast moving electron. Fast moving electron coming out of the nucleus. Sir, you may ask, sir, there is no electron inside the nucleus. How come it's possible? Yeah, there are reactions happening between protons, proton, neutrons, and neutrons inside the nucleus, and because of which electron is emitted. So that is a fast moving electron coming out of nucleus. Okay, there are different ways in which we can get electron. One is thermionic emission is there, photoelectric effect is there, cathode ray is there, and one more is what? Beta particle. Next is gamma ray. We don't say ray, we don't say beta ray. Both are particle nature, and this is gamma is a wave nature. Okay, these two are particle nature, and this is wave nature. Gamma ray is a wave nature. So what is that? It is a electromagnetic radiation. It is a electromagnetic radiation. Now, if what happens in alpha decay? In alpha decay, it emits He24. So what happens if it is alpha decay? What will happen now? In alpha decay, XZA will give what? This is the parent element or a mother nucleus, and this is Y Z minus 2 and A minus 4 plus He24. Means when a nucleus, radioactive nucleus, emits alpha particle, then atomic number reduces by 2 and atomic mass reduces by 4. So that is why it will become Y. This is daughter. This is said to be mother parent nucleus, and this is said to be the daughter nucleus. Parent nucleus and daughter nucleus. Is that clear? So we have what is that? XZA equal to YZ minus 2 and A minus 4 and He24. Is that clear? Is it clear? The alpha and the beta. Just take the screenshot of this quickly. Take the screenshot of this. Now, done. So going ahead with the next one, that is beta particle. Beta particle, what happens with the beta decay and what happens with the gamma decay? Okay. Now, in the beta decay, so in the beta decay, what will happen? See, what is that? X, Z, A will give Y, Z plus 1 atomic mass remains same. That is E minus 1, 0. Okay, or we say beta particle. Beta minus decay. This is beta minus decay. Okay, and if it is, means what? Atomic number increases by 1, atomic mass remains the same. Means it will shift one element towards right, one element towards here. It will shift two number actually behind. Okay, towards left. In this case, it is towards left. Two digits or two elements towards left. Here in this case, one element towards right. Now beta minus decay. This is beta minus, and we have beta plus decay also. In beta plus decay, what we have X, Z, A will give what? Y. Sorry, this will become X star. This is a, sorry, beta plus Y, Z minus 1 and A. It will become E plus 1, 0. This is a beta plus decay. Means like a positron. E plus 1 is a positron having the same charge, but same charge and mass, but it is negative in nature. The charge is negative, the charge is positive. Now, so this will shift one number or one digit or one element towards right, towards left, and this is gamma decay. In gamma decay, what is happening? Excited nucleus, XZA, excited nucleus will become a excited nucleus. One second. So an excited nucleus will give out gamma rays, will give out gamma ray radiation and become a stable nucleus. So this happens in the gamma decay. Is that clear? So once again, quickly see here, we have alpha, beta and gamma. Alpha and beta are in particle nature, gamma is wave nature. So gamma is wave nature. So alpha particle is the nucleus of the helium atom, beta particle is a fast moving electron which is coming out of the nucleus. There are reactions taking place inside the nucleus, because of which it is giving electron. Okay, there are some more, maybe quark particle. We will discuss about quark particles. So what exactly happens in the nucleus when there is a continuous reaction taking place. Next one is gamma ray. Gamma is a wave in nature, so it is electromagnetic radiation. So alpha decay, what is happening? So when this is XZA is the parent nucleus, when it gives the alpha decay or He2 plus, He24, then what happens here? Z minus 2 atomic number reduces by 2 and atomic mass reduces by 4. So this is the parent nucleus, the first one, and the second one is daughter nucleus. Next one is beta minus decay. In beta minus decay, XZA. So this is a parent nucleus. So when it emits beta ray, what will happen? Atomic number increases by 1. Means it will shift one digit towards right. And now in beta plus decay, it is emitting positron. Okay, this is electron and this is positron. And now it is atomic number reduces by 1. So it will shift one digit or one element towards left. And gamma decay, excited nucleus will give out gamma ray and becomes a stable nucleus. Now quickly we'll go to law of radioactive decay. Is it clear? Just take the screenshot. We'll go to the next one. Take the screenshot. We'll go to the next. Yeah. Now, clear all of you? Is it clear? No. Now, next one is law of radioactive decay. So, law of radioactive decay. Law of radioactive decay. So, according to law of radioactive decay says that the number of nucleus remaining after a certain time t depends upon the number of nucleus remaining after a certain time t depends upon the actual nucleus present at the initial time. Actual nucleus present at the initial time. Now, it is found that the number of nuclei undergoing the decay per unit time is proportional to the total number of nucleus in the sample. So, the number of, I'll write here, the number of nuclei undergoing the decay, it is emitting, like radioactive elements, they are decay alpha, beta, gamma particle, and they reduce in the nucleus. Okay, so the number of nuclei undergoing the decay per unit time is proportional to the total number of nuclei in the sample. So this is said to be law of radiative decay. So let capital N be the number of nuclei of the sample. Okay, number of nuclei of the sample. This is the initial number of nuclei, and delta n is what we can write n1 n2. If you don't want the initial, like you can also write this is the initial number of nuclei. Okay, write n1. This is the final number of nuclei remaining. Okay, number of nuclei remaining. Can we write final? We'll write final here. So what will happen? So delta n equal to what? N1 minus n2. We just take the difference. So delta n is n1 minus n2. Now what will happen? So according to the concept, what he says, according to the law, delta n by delta t in time, delta t is the time. So delta n by delta t is proportional to the actual number. N means initial number. Okay, we can write n also, initial number here. Now, so if you remove the proportionality constant, delta n by delta t is proportional to what? N. So to remove this proportionality constant, we are writing which is equal to lambda n, where lambda is said to be disintegration constant. Lambda is said to be disintegration constant. Lambda is said to be disintegration constant or decay constant. Disintegration constant or decay constant. Now, so what is that now? So if you are applying limits, if delta t is if you are applying limits, delta t tends to 0, in that case what we can write now? dn is equal to minus delta n. Why? Because it is decreasing. If it was increasing, we would have written positive delta n. Because it is decreasing, we are writing negative delta n. Okay, so now instead of writing delta n, when we apply limits, so delta n by delta t will become dn by dt, which is equal to minus lambda n. Why minus? Because it is negative, because it is reducing, not increasing, it is decreasing. So cross multiply this one and apply variable separate method from the calculus. Dn by dt is equal to minus lambda into dt. Then apply integration. Okay, once you are done with this, apply integration. That is dn by n, which is equal to minus lambda dt. From where to where? Initial to final. Initial is n0 and final is n. Here also initial is what? t0 and final is t. Okay, just take this, substitute this formula, substitute these values. Okay, now clear? So now, is it clear? Just take the screenshot. Quickly I will recap. See, law of radiative decay says that the number of nuclei undergoing the decay per unit time is proportional to the total number of the nuclei in the sample, where n, capital N, is the number of nuclei of the sample. It means initial number of nucleus. How many number of nuclei are present in the in a sample? N1, let it be N1, and the remaining is what? Remaining is N2. Just one second.